In section 8.3, we're still testing the difference between means, but this time we're going to be working with dependent samples. So the samples do matter. They are paired in some way. So it could be a before and after test or related samples. So we're going to use a two-sample t-test for dependent data. That means that we're going to have to calculate the difference between the means for the pairs of data. And we're going to have to find what we call the average of those differences. Okay, the average of the differences between the paired data. So that's what D bar means, is the average of the differences. And then once we do that, we're going to check our conditions, make sure that they're random, make sure that they're dependent, that they're paired, and they have to be normally distributed, or the number has to be greater than or equal to 30, just like before. If these conditions are met, then we can set it up using a normal model, or not a normal model, but a t-distribution model, where n minus 1 is the number of degrees of freedom. These are just the symbols used for all these things. We have n, which is the numbers of paired pieces of data. We have each individual distance between those pairs of data. We have the hypothesized mean of the difference. We have the actual mean of the differences between the paired data, which is found by using this formula right here. And we have the standard deviation of the differences, which is found by using this formula right here. So we're going to use those in our calculations. So we can use the t-test to test this difference as long as they meet those conditions using those formulas. Here's the steps written out so that you can follow along and make sure that you're doing all of the possible steps. And then we're going to start with this first example. A shoe manufacturer claims that the athletes can increase their vertical jump heights using manufacturer's training shoes. So if they use the training shoes, they should be able to jump higher than when they weren't using the training shoes. The vertical jump heights of 8 randomly selected athletes are measured, and after the athletes have used their training shoes for about 8 months, they check their vertical heights again. And then the vertical jump heights are shown in the table below. Using an alpha level of 0.1, we're going to decide, is there enough evidence to support the manufacturer's claim that their vertical heights increased? Okay, we're supposed to assume the vertical heights are normally distributed. Okay, so the conditions, they told us that they were random. They are dependent. We have before and after measurements. They tell us that they're normally distributed. So our conditions are checked. That means that we can move on to do a t-test. We're going to have to add some information to our table. So for each one of these, we're going to have to calculate the difference between the before and after measurements. And we're going to have to square those differences because we're going to use those to find other values that we need. So the difference, we're going to do old minus new. That's going to be -2, -3, 0, -1, 2, -2, -5, and -3. And then we're going to find d squared. So 4, 9, 0, 1, 4, 4, 25, and 9. Then we need to find the sum of those. So the sum of all those differences, adding all those up together, it comes out to -14. and the sum of all the differences squared comes out to be 56. Okay, we are going to find, since this is a t-test, we need to find the degrees of freedom, which is n minus 1. And since there are 8 athletes, it's going to be 8 minus 1, or 7. Now let's come up with our null and alternate hypothesis, now that we've found this information. Our null hypothesis, they're claiming that their athletes that train with their training shoes will increase their vertical jump. So that means that the mean difference is going to be when they subtract their old minus their new, they want to get a negative number because old minus new, if their new value is larger, would equal negative. So that's what makes this less than 0. That's the claim. That means the null hypothesis is that the mean of their differences is greater than or equal to 0. That means that we're going to have a left-tailed test, and that left tail, alpha, is going to be equal to 0.10. That means from the table, the t-table, using degrees of freedom of 7 and an alpha level of 0.1, we get that we have a t-value, a critical t-value of negative 1.415. That's from the table. That means that this value is negative 1.415. So now we can proceed by finding the rest of our calculations. We're going to start by finding our average of our differences. That is found by taking the sum of all of the differences and dividing by n. The sum of all the differences we know is negative 14, and we have 8. So that ends up to be negative 1.75. Then we need to find the standard deviation of the differences. And the standard deviation of the differences is found by using this formula, which is the square root of the sum of the differences squared minus the sum of the differences quantity squared divided by n all over n minus 1. This is right from your directions table, so we're going to plug in the numbers here. We know that our sum of our differences is 56. We have to square that. Or actually, we already squared it. It's just 56 because it's the sum of the differences squared, and we've already squared them. Minus our sum of our differences is negative 14, and we need to square that, divided by n, which is 8, and all of that gets divided by 8 minus 1. Plugging that into your calculator, you would get 2.121320344. That's our standard deviation of our differences that we're going to use in our standard error equation. So next, we're going to do our standard error, which is found by taking the standard deviation of our differences divided by the square root of n, which is going to be 2.121320344 divided by the square root of 8. which ends up to be 0.75000000, many zeros, and then a 2. And from there, we're going to find our t-value, which is going to be our mean of our differences minus the expected mean of the differences divided by our standard error. And our mean of our differences is negative 1.75. We expect the differences to be 0. We always expect this to be 0, divided by the standard error that we just got, which gives us a value of negative 2.3333 repeating. That is our t-value, which is in the rejection region. That means that we reject the null hypothesis. There is enough evidence to support the claim that athletes can jump higher after training using these shoes.